Today we're going to talk about spilling and a bit about memory pools and reserve memory pool and see how that works. Carol's going to present and drive the discussion. So Carol, you can take it away here.
Hello, do you hear me well?
Yeah, we can hear you.
Okay, so I will just share the presentation. Let me figure this out. Present, right? And then I need to share it somehow. Let me click here, start. Do you know how this works? Yeah, I'm looking. Okay, share screen. Okay, so do you see the presentation?
Yes.
Okay, so hello, my name is Karol Sobczak from Starburst Data, and I will give a short presentation about the spills and the memory pools and the purpose of those. So currently in Presto, there is the Presto heap memory on the worker node is divided into few regions. One of the region is the heap headroom. This is by default 30% of XMX. So this region is designated for dealing with unaccounted allocations and let's say temporary overaccounting. So in Presto, a lot of allocations for the queries is for those allocations, the memory is accounted for so that the system can keep track of the memory usage per query and per node and can react accordingly. But not every allocation is accounted, so that's why there is this heap headroom region. And apart from heap headroom, there are pools, and there are two types of pools. There is a reserve pool and a general pool, and general pool is where the queries take memory in normal circumstances. So this is a shared pool between queries. And there is also a reserve pool, which is used when the general pool is exhausted and no query can take more memory from the general pool. In that case, a single query is nominated to the reserve pool. And this reserved pool is large enough so that it can fit a single query. Like its size is max total memory per node, so that a query can proceed without having any memory obstacles until it reaches its memory limit set by the user. So the query on the node can take query allocates two types of memory, and one is the general pool. Let's go a bit back. So query can, so when a query allocates a memory during its runtime, it can either take this label this memory as a user memory and a system memory. I don't know if you are familiar with the system memory, but this is a concept that was removed from the system some time ago. Previously, there was yet another pool which was called the system pool, but it's not there anymore. However, for the legacy purpose, queries still can allocate memory and call it a system memory. And when the total amount of memory that includes system allocation and the user allocation exceeds the max total memory per node, then a query is terminated. Also, there is also another feature config, which is max memory per node, and this is the this amount of memory in this config should be is lower than the max total memory per node, and for this and only user query memory allocations are taken into account for this limit. Also, both memory kinds, system and user, are taken from the general pool, unless the query is nominated into the reserve pool. And if you have some comments, then Martin, David, then you can add some more comments here if you have something to be added.
Yeah. So I think the most important thing to mention about these configs is that this is, so the memory is accounted like per query, but the way it's actually accounted is each operator that's working on this query is going and saying, okay, we're going to take this data and we're going to put it in a hash table for a join. So therefore it's something the user controlled, we called it user memory. If it's, hey, this is a buffer that we're using to exchange data between nodes, then that was system memory. And so the idea was that we wanted to limit what users could do, not what the system decides. So we ended up with actually limits on both, I believe is where we're at right now. These two here, the per node, these are designed to catch queries that are highly skewed. So in a normal, well-behaving query, the data is evenly distributed across all the nodes. And therefore, your hash table, if you have a 100 meg hash table and you have 100 nodes, you typically have about 1 meg per node. But in a skewed query, you might have all the data on one node, in which case you'll have 100 megabytes on one node and nothing on anything else. And so if queries become really skewed, the problem is that one machine will run out of memory before everything else. So these configs here are basically designed to catch skewed queries. And I think we normally set them to some, so the strategy we normally use, I don't know if you get into this, is to take the amount of memory. If it's like 100 megabytes and you have 100 machines, that'd be like 1 megabyte per machine. And then we're like, well, we can allow the query to skew by either a fixed amount, maybe, hey, you can have a 2 megabyte skew, or maybe it's like, we'll allow it to skew by, 3x on each machine, and then we'll set these. That was my only comment. There's a question here. Is there a criteria or priority for a query to be nominated to the reserve pool? Did you get into that?
Yeah, I can go to the previous, well, there will be another slide for that, but yeah, there will be more slides on that, so we can comment then. And there are 3 mechanisms currently in Presto to deal with low memory situation. One of the mechanisms is the reserve pool. Another mechanism is there are node low memory killers. So basically, when you don't use the reserve pool, you might want some query to be killed instead. And there is also a spill to disk, which can be used on its own, but can also be used in part with reserve pool in some setups. Right. So back to the reserve pool. So like the thing is with the reserve pool that when there is when the general pool has no more memory, then one of the queries get promoted to the reserve pool, and I think it's the way it works is that the coordinator actually promotes such query, so that they don't deadlock on every node, right? So it could be that if the node would promote the query to the reserve pool itself, then on different nodes, different queries could be promoted to the reserve pool, and because other queries are put on hold, then that could result in a deadlock. Because other queries, non-nominated ones, are put on hold, that means that the cluster concurrency is reduced to 1. And this is a behavior that is often, let's say, surprising. So that's not very intuitive. We've seen cases where users were coming and saying that, hey, my cluster had concurrency reduced to 1 and it became much slower. What's happening? So you can now turn off the reserved pool and use the node low memory killer instead. And the low node memory killer can be selected via this property here. And there are 2 implementations of that killer. So I think the recommended one is the total reservation low memory killer. But maybe Dane, you can comment on that more.
David? Which one was recommended?
I actually don't remember the name, but total reservation. There's one that basically it picks the node, it picks the query to kill that will free up the most memory on the nodes that are blocked. Because what you end up with is that it's not that a query is out of memory across the cluster. It's that a few machines are out of memory because they have, maybe you have skew, so data from a bunch of queries lands on a few machines. And then the correct policy is that we found in production to use is the one that'll free up the memory on the most machines, or free up it'll free up memory on machines that are blocked.
We'll post which one it is in the chat once we look it up.
Yes, so I think the idea is that in the future the reserved pool could be turned off by default so that the Presto behaves more predictably, right, guys?
Yeah. So what we've been talking about is actually getting rid of the reserve pool entirely, and going with sorry, someone distracted me. They're going with get rid of the reserve pool entirely, and then go with having the spilling first, which we haven't gotten into, and then when we run out of, and then also have the ability to have the low memory killer for cases if people have disabled spilling. But in my mind, the spilling's the best. This problem with the reserved pool, like reserved pool worked really good in the early days of Presto when there were only a few concurrent queries. But what happens is one guy goes into the reserve pool, all the other queries can continue, but then they very quickly start to run out of memory, and then everyone is basically waiting for more memory, and you end up with a single query, and that's unacceptable for pretty much everything. So.
Okay, and do you know which query is selected, nominated for the reserved pool? Is it the query?
My memory is that it's the single largest query, and it's the first large query. There's also other problems where a query could spike up and use a lot of memory, go into the reserve pool, and then it's never moved out until it's finished. And so you end up with actually a low resource guy controlling the pool.
Right.
Yeah.
Remember, it's the query that tries to allocate more memory than is available. The
Yeah.
first guy to do that will get moved into the reserve pool.
Yeah.
There is a question. So can queries running on non-block nodes still proceed when one query is in the reserve pool?
Yes. Yes, they absolutely can.
Okay. And can the queries on the node where the query is promoted to the reserve pool also continue?
Yeah, I mean, generally every query will continue until the point where it needs to allocate memory, and the system says, hey, you can't allocate memory, you have to wait for memory to be available. So it sounds like at first blush that the reserve pool is actually going to work pretty well, But it turns out it doesn't, because what happens is everyone, you'll typically have a limit on your cluster of like, I don't know, I'm going to run 30 or 40 concurrent queries. And what happens is someone will go to the reserved pool, and you'll have, of your 30 queries, like 2 or 3 will need more memory and they'll need to wait. And then the other ones will finish, and then you'll get another batch of queries, and 2 or 3 of those will need a little bit more memory and they'll need to wait. And then after you rotate through that, within a couple minutes, you only have queries that are waiting for memory. So it's one of those like kind of concurrency blocking problems that seem really simple when you only look at one situation of waiting and you're like, oh, I got a bunch of other people. But if you look at over at time, the system effectively collects all the queries that need memory, and then you're running only one at a time, and it's really terrible.
Yeah, I think in practice it's just like that.
Going back to the policy, Piotr mentioned, he posted the name of the policy that I was talking about, the one that it frees up, it kills the query that'll free up memory on block nodes.
One comment about the which query gets picked. It's actually the biggest query. It's not the one that is asking for memory. It's the biggest one. So the memory manager will go do a sweep of all the queries, and it will pick when it decides I need to move one. It will go and select the biggest one, set it to reserve pool, and then and move it out of the general pool.
Yeah, but the query will be in the reserve pool on all of the nodes, right?
The reserve pool isn't really about nodes. It's about the global memory available in the system.
Yeah.
So it's the biggest one on using the sum of all memory across the nodes.
Okay. Yeah. Okay. So then there couldn't be a deadlock in a sense that different queries land in a reserve pool on different nodes, right?
Correct.
Yeah.
Correct. Yeah. The reserve pool avoids a weird deadlock where you have you can end up in a situation where if you only had, like, let's say 2 nodes, one query uses all the memory on node A, another query uses all the memory on node B, and then they both are asking for a tiny bit of memory on the other one, and so you end up in a deadlock. And the reserve pool solves that by picking one of them and saying, you're allowed to proceed. And so it does 2 things. It reserves a chunk of memory on every machine, and then it allows only one of the queries to proceed by saying you can now allocate from that special pool.
And that's actually, I mean, that's the reason we created a reserve pool. It was to avoid deadlocks. If we had a different mechanism, it wouldn't exist. We have gone with spilling or something like that.
Yeah, and as I said, it sounds really clever at first, but in practice, it doesn't work because you end up having this single-threaded problem, and you're also reserving a big chunk of memory on every machine that you don't actually want to be used because you don't ever want to enter the reserve pool.
So I have a question. So why didn't you implement out of memory killer from the start?
That was so we at first we said, well, we don't want to be killing queries. Like, we don't want to have people have bad experience when the cluster runs out of memory in terms of their queries suddenly dying with no good reason. So we said, basically, we want every query to succeed, and we thought this approach seemed reasonable, and it was reasonable at the time. And then, well, it turned out it didn't work very well in the long run. So it was mostly about user experience.
Mm-hmm. Okay, makes sense.
I think it's Piotr from here. I think this still has its applications, like when you don't really care about the concurrency and you do some single one-time ETL jobs, then the fact that you are using ReservePool is not a problem, and you might be you may get away without configuring your Presto cluster carefully, because when you use low memory killer, really is useful for concurrent use cases, as Dan said. But then you actually still don't want your queries to be killed, and you need to configure resource groups appropriately so that you don't run into a situation when you over abuse your resources. So with ReservePool, you can avoid all of this configuration effort.
I think the better solution to this is spilling, which yes requires a configuration to set up the directories, but I think spilling is a much better experience. Well, actually, let's kind of like back up. Like, this all works assuming you have more resources than you need at all times. So like, you can set up any of these, and actually, like, this is what we ran into when we first set this stuff up, was we actually had plenty of resources, and therefore, like, none of these actually triggered. So in a low resource situation, the reserve pool, it works as long as a single query can use all the resources of a system. But typically what happens is the queries that are big enough to hit the resource limit end up being weirdly skewed. And so you end up with a query that's in the reserve pool, but actually not using a lot of CPU, and ends up taking a really long time because it's skewed, because skewed queries almost always take a long time. And so then you're in a single threaded, I'm not using my resources for a long time, and the users get really mad because they see the systems not being utilized and they're waiting in a really long line. Whereas spilling, I really like, because what it would do is end up effectively punishing that one query that's slow and poorly written, so it's skewed, and where everyone else gets to move along really nice. The killer is another form of that, and it generally picks the poorly written queries to kill, or the highly skewed.
And I think there is also another reason why out-of-memory killer worked at Facebook, right? Because you had a nice mechanism for restarting queries, right?
Yes, yeah, absolutely.
So then the query gets scheduled again, but this is probably something that average user won't have in place, and he must rely much more on Presto for queries to pass, right? Because the automation won't be that sophisticated, I guess. Okay, we can move to the next slide. So, so with the spill, there came another concept, which is the revocable memory. And revocable memory, so like previously you had system and user allocations, and now you also have revocable memory allocations. And those allocations take chunk of the general pool. And they are not taken into account for the query limits. So when you have a query that is spillable, it can take almost, and there is no concurrency, it can take up to entire general pool. But of course, when another query comes in and wants to allocate some memory, then such revocable memory has lower priority. And such memory will be spilled by operators that support that. And so currently there are 4 operators that support spilling. This is the aggregation, which was the first that did support spilling. Then there was join, and in the Presto CQL version, there is a support for spilling for window operator and also for order by operator. There has been a lot of improvements to the spilling in the 300 series of releases. So there were a couple of bugs that prevent spill from working, and there were not much, let's say, instrumentation to monitor the spilling. So at the moment, in the current releases, you also can monitor how much revocable memory query takes. One thing is that when you enable the spill and you have a reserved pool enabled, it might cause for the queries to progress very slowly. So where you have So when you have a large query max total memory per node, then revocable pool is big and the general pool is small. And Spill, of course, will try to prevent queries from entering the revocable pool. Spill generally works only for the, so when the general pool is small and it begins filling to the limit, then Spill will trigger, and instead of for a query to go to the reserve pool, it will constantly spill, and we have observed such thing. So some clients have observed and noticed that queries progress very slowly. So in cases when the reserved pool would be big and Spill is enabled, we actually recommend disabling the reserved pool and leave only Spill, so that the queries progress much faster. So what Spill is not, so you still have to have a cluster which have reasonable memory. That would be more than, I know, not much, but more than 60, like more than 64 gigabytes, probably like something around 90, 100 minimum per node. And Spill won't work with very small values for the query max total memory per node. So because not every operator is spillable, and even for the operators that spill, they still require some non-revocable memory to progress. That means the max total memory per node should still be reasonable. And obviously, not operators are supported. And not plans also. Not plans are spillable. So, for example, when you have a broadcast join, then joins in the source stage won't be spillable. This is because enabling spill for them would hurt the performance of the query when spill is not triggered. So this is probably important when you when you have spill enabled, but spill is not triggered, you don't get a performance penalty. So you can actually enable spill in your workloads. You should be able to enable spill in your workloads by default. And there, for example, also operators like Windows, they support spill, but you still need enough memory for a single partition to fit. When such partition doesn't fit, the query will still fail with out of memory. So those are limitations. However, when you have a mix of queries, and let's say concurrent workloads with different kinds of operators, then spill should work nicely, because then it can revoke memory from different queries, and there will be the granularity, it will be lower, and it could cope with larger query peaks. And there is one observation for the how workloads, let's say how workloads look like. So often workloads have a long tail. So this in this slide you can see the example of the workloads from the Facebook, and you can see that majority of the queries finish very quickly. Actually, the X scale is logarithmic, and only few queries are very long. So even though that's for time, I would expect for memory to be kind of similar. So like most of the queries are really small, and there are a few queries that are large enough, and please correct me if I'm wrong here. So because of that, if you take that into account, then for most of the time, the cluster resources should be fine, but then there might be some rock queries that come in, like large ETL or skewed aggregation or something like that, that can saturate the memory and could, if the reserved pool was enabled, could reduce the concurrency or could make the queries to fail. And Spill enables you to deal with such rock queries. So when you have a peak of queries, or when you have such large rock queries, then you can use Spill. So you can rely on Presto more for the queries to pass instead of failing. And you can also adjust your resources better. So you don't have to prepare for the you don't have to prepare your hardware for the peak utilization, but you can choose the hardware to deal with some. It doesn't have to be adjusted for the peak, but can be adjusted more for an average, maybe. Maybe not for average, but definitely not for the peak. And this way you can also, save the resources. And I think Dane also mentioned that the query that I don't think it's the case at the moment, but you can also, you can design your workload in such a way that you can enable Spill for only some category of queries via I think the resource groups can support that. Or you can set the Spill property explicitly so that when you have queries that you expect might take a lot of memory and you don't want to penalize the other queries that that should finish quickly, then you can enable Spill for only subset of the queries. This way, you accommodate both type of queries and they should all complete successfully. And you don't saturate the cluster. So in order to enable the Spill, you have to set few properties. There is a main toggle, which is the Spill enabled. This is the Boolean toggle. And there is also a session property of the same name, I think, with the underscore. You need to specify the Spill paths. So the Spill path is actually a list of paths separated by the comma, if I recall correctly. And this way you can Spill to multiple disks. So you can implement a schema called just a bunch of disks, where you choose multiple disks to improve the Spill Spill performance. In a cloud environment, though, I don't think you need to choose a lot of paths, because, for example, in AWS, you will get more IOs the bigger EBS is, for example, right? You shouldn't use system partition for Spill. Now, the last two properties, memory revoking threshold, that's the threshold when the Spill is triggered. So when you have a general pool and the memory allocations of that pool exceed that threshold, by default the threshold is 90%, then Spill will be triggered, and the spilling scheduler will try to reduce the memory usage of the pool to the target value, right? So when the total memory reservation of the general pool reaches 90% by default, then the scheduler will try to reduce that by default to 50%. Yeah, and that's it. If you have questions, comments, then you can ask. There are questions, actually. Let's see Let's see the questions. Okay, no questions. Do you have some questions?
I had a comment about enabling spilling and when to do it. So having a low memory limit for queries is actually can be a safety mechanism. So when you just have users submitting all sorts of like random queries that they're developing, they'll often make a mistake and actually do something that would cause a query to use like effectively infinite amounts of memory. Like they'll group by something that has trillions of values. And so by default, we found that you actually want to set a relatively low memory limit. And only once you've verified that the query actually needs that memory and it's not a mistake, then you go and raise the limit. So if you say just like enable spilling for everything, you can end up like wasting huge amounts of resources, spilling stuff that you would actually have wanted to fail much earlier.
Mm-hmm. Yeah, makes sense. So maybe.
Kind of,
Mm-hmm.
Sorry, I had a question. This spilling only supports local disks right now, right?
Yeah, there is no support for S3, for example.
Okay, and it's so I think at some point we talked about having that sit behind some interface that eventually we could put as a pluggable interface, so that people, let's say someone that runs in AWS could write a plugin that would spill to S3 or some other system. So if someone was running on an on-prem scenario, they might have a different remote storage system and they might want to plug that in. So that's something that we should probably consider as we start productizing this more.
Yeah, that's true. I think like systems like S3 should be a good target for spill, because at the moment you have to, if you want to use spill in the cloud, you have to provision the machines with some EBS storage probably, and then you need to estimate, let's say, how much storage you want, and it requires some prior thinking, right? And with S3 it's much easier, for example.
So Carol, you mentioned spilling on EBS. My experience with EC2 might be outdated here, but do you actually want to use an ephemeral disk or EBS or both? And like, why would you choose one versus the other?
Well, you could use the ephemeral disks too, but I think from the point of automation, it would be easier to use EBS because they are much easier to attach and to plug them in. But of course, you are not limited to only EBS. We also don't recommend at the moment to have dedicated machines with hardware for spill-enabled queries. Like you can have, for example, instances with SSDs, but since you already paid the penalty for the performance when spill is enabled and hit the spill, this won't change that much, I guess, for you. You want the query to pass and not pass quickly, right? So if it's just a bit slower or twice slower, then maybe you don't care, right?
So you found that EBS is substantially faster than the ephemeral disk?
Well, we didn't do that benchmarks actually. So I think it might be cheaper. I have a question. Did you try to use spill at Facebook, actually?
No, well, we would have had to write the plugin implementation because the compute machines don't have storage on them. So the only storage is remote. And like in general, the clusters were, extremely large. I mean, well, I don't know about extreme, but they were large enough that we could run queries in the multiple terabytes of memory range. And pretty much, it's pretty rare to have a well-written query that uses more than a terabyte of memory. We ended up not really needing it. And then to deal with situations where the system got stuck, that's why we wrote the killer. Because really it just came down to concurrency in the systems we retried. For interactive systems, like I don't think we really ever run in. We just interactive systems had much lower memory limits. I don't know, 500 gig or something like that. Basically the comment was, if you're running something that needs more memory than that, then it's not interactive. Like you push them into a batch cluster.
And I think there is also another mechanism to deal with low memory situation, but I didn't list it here. So there is the group execution, right? Which I'm not sure what state it is exactly. Is it experimental or is it productized that you can rely on it? What's the state of that?
So the grouped execution, the issue with grouped execution is that if it works, it's great. And what grouped execution does is, if you have a query, and I'm just going to talk about Hive here, it can apply to other systems, but if you have a query that is aligned with the partitioning of the table. So
I think it's bucketing.
Sorry, bucketing, yes. So if the table is bucketed on user ID and you're doing a grouped aggregation or a window function or something like that.
Or join on user ID.
Or a join on user ID, then, and both, for a join specifically, if both tables are bucketed on user ID and have compatible bucketing, then it will pick up effectively one bucket at a time and join those two buckets together. And with that situation, you're only picking up 1 over the number of buckets in the table amount of memory. And so this works great until you run into a table that's not bucketed. You run into a table that's, you run into a query that isn't aligned, and which is really, really common because it pretty much requires people to think ahead. Now, the biggest tables should be designed to have queries go work effectively against them already, but well, the other issue is that you can only choose one bucketing. So if you're going to join a table based on user ID, and in another case you want to join on, I don't know, advertiser ID or something like that, you got to choose one, and only one's going to be work with that strategy. But it is running in production at Facebook, if I remember.
Yeah, and I think there is also a difference that you need to tune the amount of concurrent buckets that are running at the same time, right? So you might end up setting the value too low or too high, and when the value is too high, then you might still run out of memory, right? And when the value is too low, we don't utilize you pay the penalty for having bucket exits enabled, right?
And in addition to that, a single bucket has to be executable on a single machine. So it won't do, for like an aggregation, it won't do use distributed memory for that bucket. So if you're grouping on user ID, all those groups need to fit in a single node for this feature. I mean, in general, Presto will use distributed memory. So that solution could be used in a scenario where you have really large buckets and the system processes like one bucket at a time and then distributes it across distributed memory. But that isn't how it works.
Mm-hmm. Yeah, that's good.
We had a comment from Mark. Iceberg improves this a bit. You can bucket on different keys and they don't get hashed together. This supports diverse workloads. Does that, do you end up having multiple copies of the data in that case?
So this is just based on my reading of their document, and is no. So the issue with Hive is that when you bucket on, say, member ID, and let's say we have a graph and we bucket on like member ID source, member ID destination, it's actually hashing both of those together rather than hashing the source, hashing the destination, which would let you say, you know, you can, it lets you make trade-offs between how finely bucketed each dimension is.
Yeah,
maybe multi-level.
yeah. If I remember, it was like a multi-level hash. So they'll hash one way and then hash again.
Yeah, it's essentially like Iceberg's model is that you essentially have like a projection expression where you have a set of columns that are expressions of your table columns, and one of them is hash. I have a bunch of notes that I went through looking at how to adopt some of those changes. One of the issues I've been running into, and I'd be curious to hear people's takes, is once you introduce like more flexibility, there's a lot more opportunities where we have to decide, do I scan all the buckets in parallel, or do I try to scan along one dimension? Because I think sometimes that might be like, it'll take less memory, but be more efficient. Especially, Dane, you gave the example of every bucket has to be processable on one node. And so what we've seen actually is we'll enable a table and it'll become bucketed. And then because it's bucketed on a few buckets, all the queries slow down because they're not scanning at the same speed. So I'm curious in sort of a general sense, how people want to like expose those options either within the code or up to users of choosing between efficiency, speed, stability, that kind of thing.
So my memory is we ran into like that exact same issue, and basically, if I remember, like we pushed all the people who had tables that had low numbers of buckets to be like 500 plus. I think we always use powers of 2, so I think it was like 512, but pretty much the people who wanted to do this, they were like in the 1,000 to 4,000 buckets per partition. So, and that worked well for most things, but I think you would run into an issue with, like, again, there's this part where it's like, it's not big enough, where the data is so small that you end up with like too many small files, and that hurts performance. And there's, I don't know. Yeah.
That's actually how we discovered it. We had a table that was partitioned on day, and so it had, you know, thousands of partitions, but then only like 5 buckets.
Yeah.
And that went back to the partitioning thing. I'll share some of my notes on all this, and I'd love to get people's feedback on it.
My other thought on this was that I think this is a place where the cost-based optimizer may be able to help. To me, it's similar to the problem of, if I'm going to write a table that has a lot of buckets, or I'm going to write a lot of partitions in parallel, I end up with, currently, because we just randomly organize the data across the writers, we end up with too many concurrent open files, and if you're writing in a columnar format, every one of those writers needs a large amount of memory. And so it would be, this is a place where I'm hoping the optimizer will be able to help and give a decent estimate of the cardinality of like the number of partitions or the number of buckets. And if we have a reasonable estimate of that, then I think we could make a better decision about targeted enablement of these different features.
Note that Presto now supports bucket evolution. So if you bucket a table on too few buckets, as long as you double it or increase it by a power of 2 relative to the previous one, you can expand the bucket count for new partitions without having to go back and rewrite all the old partitions.
Yeah, I think like also the bucket execution is kind of hard to enable. because you need to, if I recall correctly, enable the collocated joins, and then you need to enable some other properties, which are not, let's say, obvious that they are related to bucket execution at first glance. So it's not as easy to enable as, let's say, spill.
I don't know why we don't have collocated joins on by default.
We should look at that.
Yeah.
Yeah, we should definitely improve the documentation in this area.
Yeah.
One comment, Dane, you compared the bucket execution for reads and writing. They are quite related, but the difference is quite important. When writing, you may not have hard time knowing number of buckets upfront or number of partitions, because it can be from data source that from other data source, and you simply couldn't know. And
Absolutely.
for bucket executions, you should be able to know the number of buckets very well and compare this to number of nodes and determine whether it makes sense to assign buckets to nodes or to repartition. So the problem looks much more static from a planning perspective.
Mm.
It should be much easier to attack.
And if you could, for example, estimate the amount of concurrent buckets that should run at the same time, that would also be very great. Yeah.
So there are other complexities that need to be taken into account. Like if you run bucket execution, you may because a given bucket needs to be processed in one machine, you may not have enough memory to process that bucket. Whereas if you were running in non-bucket execution, the data may be spread out across more machines or something. And
yeah, but this limitation is not inherent, Martin, as I understand, because this is our architectural decision that the bucket needs to be assigned to a single machine. And you could imagine that you still process one bucket at a time, but you do repartitioning further.
Yeah, that's when we implemented bucket execution, we started with the bucket in a single machine because it was the easiest.
Yeah.
The other approach requires changes to the execution engine, changes to the planner that we didn't want to take on at the time. So it's a much more complicated thing. Oh, and comment about at Facebook, we were running bucket execution, but it was on a case-by-case basis. It was we basically told people, if your query runs out of memory, turn these options on, or we would turn them on for them. But it wasn't like enabled like across the entire cluster for everything.
Yeah. At this point, it's considered a power user feature.
Yeah. So I don't know if I would call still power user feature at the moment. Maybe it's less power actually because it's easier to enable. So if somebody would like to try it out or play with it or use it in their workloads, that would be great. And if you find some kind of issues or bugs, then please report them back so that we can fix them. I think at this point it should be stable and ready for the let's say serious workloads. But obviously feedback is welcome.
Hey, Carol, is there anything in the query events or metrics that will let us sort of see if this is taking effect? We've had a few cases where like things go into the reserve pool or scene2 in the middle of the night, and then we go and try to piece together what happened. And I'm just curious if what's there for.
So we have added additional query statistics to the on various levels, right? So now I think starting from the operator level, you can see how much revocable memory it uses. What's the peak of revocable memory? I think on the, maybe Piotr could help here, but I think on the query level stats, you can see the amount of spilled data per query. Maybe it's also, maybe you can also get the stats for the operator level statistics. But generally, you get the metrics for the revocable memory now, and you get the metrics for the spilled data now. So when the spill is triggered, the spilled data should be non-zero, and you can also see that from the user interface on the detailed query page. And you can also on the other side, you can also see how much memory is revocable per query. So you can, let's say, see that if that query is spilled, then you could save 50% of that of the memory that this query uses. Right? So you can see which queries are, let's say, spillable also.
One follow-up question kind of for everyone. We only have a couple minutes left. Maybe just ping me offline. Is one of the things we're talking about is actually removing the reserved pool entirely, because it causes a bunch of internal problems. And we find that people don't actually, when it triggers, it always seems to trigger in the middle of the night, of course. And then they're surprised by it, and it doesn't actually end up really doing anything they want. They end up restarting their whole clusters to clear out the bad queries, or you just kill a bunch of queries until everything starts going again. So our idea is to remove it and enable basically the killer and or spilling. Spilling's a more complicated subject because we talked about it. So if you're using the reserve pool and really like it, talk to me and let me know what the use case is, or let Carol know, or any of us.
Yeah, I think we should just disable it by default for first and see what happens. And it's really important to enable the killer at the same time by default, otherwise you will get stuck. And unfortunately, you cannot enable spill by default because you don't know where to spill, and there might be no place for spilling. And one more thing about the strategy. Currently, the strategy to pick up the, maybe this is obvious for everyone, but it might not be. The spilling is something that happens on a node, and it's not a global decision, unlike killing more biggest query or promoting to reserve pool. Spilling is local decision on a node, so it has capability to gracefully handle the skew. And the current policy is to pick the oldest query that has an irrevocable memory, of course. So among the queries that have revocable memory, have spill enabled, we are choosing the oldest one first. And of course, this is not one solution fits all. And currently, this is not pluggable, but it shouldn't be a problem to make it pluggable. I will just post a name of the class we'll look into if you are interested. And then we can extend this adjust so that it fits more.
Okay, we're out of time. So if anyone has more questions or comments, let's continue discussions on the Slack channel. So thanks everyone for joining, and thanks Carol for preparing and presenting on this topic.
Thank you.
Bye everyone.